We've been talking about epidemic diseases and how they spread on networks, and our plan here is to analyze what's maybe the most basic mathematical model of epidemic disease, the branching process model. So the idea here was that we have an initial patient, patient 0, and they meet K people in this big crowded city, and each of them meets K new people, and that just keeps going on forever, and that builds us this branching contact network. And then a disease spreads on it, right? And each person infects each of these K new people that they meet separately, independently, with probability P. Okay, the basic question we'd like to ask is, faced with an epidemic, which is characterized by this branching factor K and this probability P, will the epidemic have a non-trivial chance of actually running forever, right? Infecting people in arbitrarily deep waves, or will it almost surely die out in a finite number of steps and then the rest of the population is safe? And the answer to this question depends on P and K. And it's going to actually have a very nice clean answer in terms of P and K. To build up some intuition for that, let's think about the role that P and K are playing here, right? So clearly, larger values of P are more dangerous because P is a chance that when you come in contact with a sick person, you get sick. Right? So a large value of P means this thing is just spreading very reliably. You meet a sick person, you are almost surely going to get sick. A low value of P means this thing is not very contagious. It moves sluggishly, and so it has a hard time spreading through the population. Similarly, a large value of K is dangerous because it means this sick person has entered a very crowded city. They meet lots of people, large value of K. Those people meet lots of people, and so the thing has just lots of potential ways to get into the population. Whereas a small value of K means it's sort of a sparser population and just there are fewer chances for the disease to spread. So large P is bad, large K is bad. And it turns out that what characterizes the behavior of the epidemic turns out to be the product of those two numbers, something that epidemiologists call the basic reproductive number, which they denote by this R sub 0. Okay? So R0 is P times K. And P times K has a very natural interpretation. Because if you're someone who's infected with the disease, you meet K people, you infect each of them with probability P, then the expected number of people that you're going to infect is P times K. Or if you think about it from the disease's point of view, right, the disease is residing in this person, the expected number of new cases caused by this person is P times K. So in some sense, the relation of R0 to the number 1 is important because you take this one person and instead now this one person has been replaced by R0 new cases of the disease in expectation. So in particular, if R0 is less than 1, then the disease is not fully replenishing itself. Right? You take the one sick person and in expectation they produce fewer than 1 new cases of the disease among all the people they meet. But if R0 is bigger than 1, then the disease is actually more than replenishing itself, right? Because you take the one sick person and in expectation they produce more than 1 new case of the disease. And it turns out that R0 versus 1, that is the knife edge that characterizes whether the disease has a chance of spreading forever. And in particular, the basic mathematical fact about this model is the following dichotomy. It says if R0 is less than 1, then the disease dies out in a finite number of steps with probability 1. Okay, so with probability 1, it will end a finite number of waves, and the entire rest of the population is safe, is completely healthy. Whereas on the other hand, if R0 is greater than 1, then there's a positive probability that the disease will actually persist indefinitely. In other words, that it will infect people in arbitrarily deep waves, arbitrarily far down the contact network. Now, if R0 is greater than 1, right, even if it's very large, as long as P is less than 1, we can't guarantee the disease will persist indefinitely, right? Even the most super powerful disease can just get unlucky, right? Patient 0 meets K people, and it has a coin that's really biased to come up heads, but the coin gets flipped K times and they all come up tails. A very unlucky event, the disease is over, right? With patient 0, it ended, right? Unlucky for the disease, lucky for us, the human beings living in the city, because no one got sick. So we can't say it will definitely go forever. But despite all the obstacles that the disease faces, all those coins that could come up tails, if R0 is bigger than 1, there is actually a positive probability that it will live on forever, continuing arbitrarily deeply down the contact network. So R0 is this number that you want to think about when you want to think about how aggressive is this epidemic, at least when we're talking about this simple, clean branching process model where everyone goes and meets k new people. And so as a result, when we think about, say, measures for controlling disease, reducing the basic reproductive number can really be a big deal. And it can be a particularly big deal if you're trying to push that number from, say, being above 1 to being below 1. Now, suppose you were faced with the question of reducing R0, right? You're faced with a disease that's entered a population, and you would like to bring down the basic reproductive number. Well, it's a product of two terms, so you can work on either one of them. You can work on reducing p, or you can work on reducing k. And in fact, you actually see lots of public health activities that can be interpreted as either reducing p or reducing k. In fact, p times k is sort of a nice lens through which to interpret a whole bunch of interventions that people would take when there is a disease. So, for example, how would you reduce p? You want to make it less likely that a contact between two people results in contagion, right? So during this could mean better sanitary measures, right? During flu season, it could mean put hand sanitizer in lots of places where people are eating food to reduce P. So for example, during flu season, sometimes on the Cornell campus, you see people put up signs that say, when you see your friend, instead of, hugging them or even shaking hands, consider, a fist bump because it does fewer, the germs don't spread as much that way. And, that was sort of one of the sort of public service announcements that you would see posted around the Cornell campus. All of this is reducing P, right, through all sorts of different measures that people invent to try doing that. Or you could reduce K. And reducing K also has this very natural interpretation. It's sort of what we think of as, in the extreme case, quarantine. I would like to keep people from coming in contact with each other, right? So if there were really this dangerous, out-of-control disease, you tell people, to the extent you can, stay home. Don't assemble in big public places. Because if you assemble in big public places, you're increasing K. And again, during flu season at Cornell, for example, the public health team at Cornell actually thinks about, can we sort of convince, fraternities, for example, not to have gigantic parties, at the absolute peak of flu season, because that's going to bring a lot of people into contact, and it's going to cause the epidemic to suddenly have much bigger branching factor, right? And those things can actually work because they actually are working on the thing that's controlling the spread and ultimately the success of the epidemic. So what that says is even this very simple model of people going out into a crowded environment, meeting new people, and the disease spreading, it gives us, first of all, a very concrete way to characterize the ultimate fate of the epidemic. And it also, therefore, gives us knobs that we can turn and ways in to actually think about how we might intervene, right? To either reduce the contagiousness of the disease itself or to alter the contact network so it spreads less aggressively.